Among the countless stars shimmering in the darkness of space, many host their own planetary systems. Some worlds are scorched by the relentless heat of their stars, while others are locked in perpetual twilight and ice. Yet hidden within this cosmic grandeur may lie planets whose conditions bear a striking resemblance to our own Earth. On these planets, vast oceans could stretch as far as the eye can see, clouds might glide across the sky, and flashes of lightning could illuminate distant horizons during thunderstorms. It's tempting to believe that life has found a way to flourish there, just as it once blossomed here on Earth, in its oceans, forests, deserts, and at the icy poles. And yet, life itself remains one of the most astonishing, complex, and mysterious phenomena in the universe. Despite thousands of years of study, we still lack answers to many questions. The biggest being, does biological life exist anywhere beyond Earth? And if it does, where should we look for it? And how would we recognize it? In pursuit of answers, humanity has undertaken extensive investigations of planets circling distant stars, exoplanets that could potentially resemble our own world. Astronomers have already confirmed the existence of thousands of these enigmatic objects. Some orbit old, faint stars, while others circle young giants that emit overwhelming energy. Yet in evaluating each new world, scientists specifically look for signs of water, an essential suite of chemical elements, and moderate temperatures, the very conditions that make life possible as we know it on Earth. To gauge how Earth-like a particular exoplanet might be, researchers have developed a special measure known as the Earth Similarity Index, ESI. Let's explore what it is, how it's used, and how it relates to one of the most intriguing exoplanetary discoveries to date, Kepler 452b. The Earth Similarity Index, ESI, is among the simplest and most common tools for a quick assessment of how closely an exoplanet's basic characteristics match those of Earth. At its core, the ESI involves two key parameters, the first being surface gravity. It's calculated from a planet's mass and radius. If the gravity is significantly higher or lower than Earth's, organisms similar to those on our planet might face serious challenges in terms of body structure and metabolism. The second factor is temperature, which is derived approximately from the planet's distance to its star and the star's brightness, or luminosity. If the temperature is too low, water remains locked in ice. If it's too high, water can only exist in vapor form. Both extremes are unfavorable for Earth-like life. Combining these parameters yields a single score that reflects the degree of similarity to Earth. However, this metric has clear limitations. It does not account for other key characteristics, such as stellar activity and orbital nuances. Red dwarfs often unleash powerful flares that can strip away atmospheres and intensify radiation exposure, while massive stars, like Sirius or Vega, live too briefly for complex life to develop. Orange and yellow dwarfs, such as our Sun, are generally considered more promising hosts. If a planet orbits too close to its star, it can become tidally locked, leaving one side perpetually scorched while the other remains in darkness and cold. Conversely, if it lies too far away, it risks freezing beyond the habitable zone. Despite these drawbacks, the ESI is a convenient, quick filter because calculating it requires only basic information about a planet's mass, radius, and orbit. Earth naturally serves as the gold standard by which we judge conditions capable of supporting life. Kepler 452b was discovered by NASA's Kepler Space Telescope, launched in 2009 to detect planets around other stars via the transit method. The principle is simple. When a planet crosses the face of its star, it blocks a small portion of the star's light, causing a slight dip in brightness. By measuring these dips, astronomers can estimate the planet's orbit and approximate size. In 2015, NASA scientists announced the discovery of a planet designated Kepler 452b. Why did it spark such excitement? The star Kepler 452 is very similar to our Sun in spectral class, and Kepler 452b orbits within the habitable zone, far enough from the star that, if it has a suitable atmosphere, liquid water could exist on its surface. Additionally, its radius turned out to be only about 1.5 times larger than Earth's. All of this led researchers to speak of potentially Earth-like conditions. Kepler 452, the planet's host star, is located about 1,400 light-years away in the constellation Cygnus. Its spectral type is G2, practically the same as our Sun. However, astronomers estimate that Kepler 452 is about 1.5 billion years older. This makes the system particularly interesting. If the exoplanet has remained in a habitable zone for so long, life there could have had more time to arise and evolve, assuming other conditions were favorable. Kepler 452's mass and luminosity are only slightly higher than the Sun's, and its surface temperature is comparable to solar values. In terms of chemical makeup and evolutionary path, Kepler 452 follows a similar pattern, but is at a more advanced age. Scientists often refer to such stars as solar twins, pointing to their significance in the quest for life-bearing worlds. It's believed that Kepler 452b completes one orbit in around 385 Earth days, meaning a year there lasts about a month longer than ours. Calculations show its orbital radius is just a bit larger than Earth's, placing it slightly farther from its Sun-like star than we are from ours. Thanks to Kepler 452's slightly greater brightness, the planet may still receive roughly Earth-like levels of energy, maintaining a similar energy balance. Of course, there are many unknowns. We lack precise data on heat distribution, axial tilt, and possible moons. Even so, the mere fact that this planet's year is close to 385 days, coupled with its location in the habitable zone, sparks the imagination. We can't help but picture what it would be like if we were there, how much longer the seasons might last, and how different their cycle might be. Kepler 452b's radius is about 1.6 times larger than Earth's. On one hand, this leaves open the possibility of a solid surface rather than a purely gaseous envelope. On the other, such a larger radius may indicate that the planet is closer to a mini-Neptune or a super-Earth with a thick atmosphere and strong gravity. Determining its mass is difficult, but models suggest it could be 5 or 6 times Earth's mass if it's mostly iron and rock. Its internal structure remains a mystery. It could possess a hot iron core surrounded by a silicate mantle and crust, or perhaps it contains extensive layers of ice and water if it formed farther from its star. Its substantial size increases the likelihood of a dense atmosphere, yet we don't know if this atmosphere is breathable, toxic, scorching like Venus's, or something entirely different. As soon as scientists announced the discovery of Kepler 452b, media outlets splashed headlines about Earth's twin and New Earth 2.0. However, experts advise caution. While the orbit and star of Kepler 452b appear promising, countless factors ultimately decide whether a planet can be hospitable to life. A key question is the atmosphere. If a runaway greenhouse effect has developed, the planet may be superheated like Venus. Conversely, if the atmosphere is too thin, stellar radiation could overwhelm its surface, or the water could simply evaporate into space. A planet's magnetic field, crust composition, and tectonic processes are also critical, but currently unknown. Even so, the fact that it lies in a habitable zone around a sun-like star gives hope for favorable conditions. Since the Kepler mission, other space observatories and ground-based telescopes have added Kepler 452b to their watch list. Instruments like the Hubble or Ground-Based Very Large Telescope (VLT) systems can at least refine what we know about its star and look for subtle gravitational effects. However, a full spectroscopic study of the exoplanet's atmosphere is still extremely difficult. Kepler 452b is simply too distant, and its star not bright enough for current technology to analyze in detail. Still, the future holds promise. Next-generation telescopes, such as the James Webb Space Telescope, and planned giant Earth-based observatories boasting mirrors over 30 meters in diameter with advanced coronagraphs may eventually reach the precision needed to probe certain atmospheric traits of Kepler 452b. Detecting water, oxygen, or methane in its spectral data would be an exciting hint of biological activity. This work is daunting, but technological breakthroughs over the past decade inspire optimism. If Kepler 452b has indeed sustained a stable climate for hundreds of millions or even billions of years, evolutionary processes akin to those on Earth might have had more time to unfold. Since its star is older than the Sun, this world could have had a longer window to develop, or conversely, to run out of resources. Hypotheses abound, but none can replace the certainty that direct observations might bring. Then again, life on this planet, if it exists, might be drastically different from our own biosphere. There is no guarantee of photosynthesizing plants or carbon-based chemistry. Life could have found an entirely different path. Nonetheless, such possibilities fuel advancements in astrobiology, inspiring improvements in our search techniques for habitable worlds, and guiding us to learn how common Earth-like conditions might be throughout the cosmos. The idea of sending an expedition to Kepler 452b is mesmerizing, but at 1,400 light-years away, it lies beyond the reach of any technology we currently possess or might have in the near future. Even traveling close to the speed of light, the journey would take well over 1,000 years. Science fiction, however, loves to explore concepts of generation ships or revolutionary travel methods, keeping the dream alive. For humanity, the very existence of such a nearly Earth-like planet at that distance highlights the vastness of the universe. If these worlds are real, then perhaps somewhere among them are beings who have passed their own prehistoric era, discovered science, and built telescopes to look for fellow, intelligent life. This thought inspires us to push research further, never losing hope that we'll someday gather more direct evidence of life around the corner. Essentially, Kepler 452b is but one among thousands of exoplanets, yet it vividly illustrates a compelling idea. There are worlds out there that might be very much like ours. Each system, however, has its own story, and each planet its unique conditions. Observations of this distant super-Earth reveal how relatively small differences in radius and mass can profoundly alter a planet's fate. Perhaps it's home to temperate climates, or perhaps it's scorched by unbearable heat or beset by endless storms. Still, Kepler 452b's discovery bolsters our view that Earth is not a singular exception, but rather one of many celestial bodies capable of sustaining life. Direct data on its atmospheric composition, surface temperatures, or magnetic field remain a matter for the future. Yet even now, this planet expands our horizons, sets the stage for new missions, and drives scientists to search more intently for second Earths. One day we might find not just one, but dozens of potentially habitable planets, each with its own remarkable tale of how life can flourish among the stars. If you enjoyed this video, don't forget to give it a like and subscribe to the channel. It's the best way to show your appreciation for my work and inspire me to create more exciting content for you. Among the many enigmatic bodies populating our cosmos, one stands out in particular: Titan, a large satellite of Saturn, cloaked in a dense atmosphere and wrapped in cold, mysterious skies. At first glance, it resembles a mini-planet lifted straight from science fiction. Orange-tinted clouds, rivers and lakes of liquid hydrocarbons, strange cloud formations, and rugged mountains stretching toward unknown horizons. It is no exaggeration to say that Titan is among the most remarkable corners of the solar system. Indeed, it's the only known moon with a thick atmosphere and an entire network of methane seas. It's hardly surprising that it has drawn such keen interest from researchers. Every fresh image of its surface opens another chapter in this captivating cosmic story. But what truly sets Titan apart? What forms of life, if any, might lurk beneath its faintly discernible clouds? And why does Titan play such a pivotal role in understanding the evolution of celestial bodies and possibly life beyond Earth? Let us journey through the fascinating history of Titan's investigation and explore its main features, ranging from geology to atmosphere, and from chilling vistas to hidden subsurface puzzles. Although Saturn itself was known to ancient astronomers, Titan was discovered in 1655 by the Dutch mathematician and physicist Christian Huygens. Through a telescope of his era, he observed Saturn and noticed a faint companion orbiting it, evidence that this was indeed a moon. For the 17th century, it was an epoch-making event, revealing yet another moon-like object beyond the Earth-Moon system. For many years, ground-based observations failed to show any clear details of Titan's surface, as it lay concealed beneath a thick, hazy shroud. By the mid-20th century, however, scientists began to suspect that the atmosphere was both dense and rich in nitrogen. Definitive proof arrived in the 1980s, when the Voyager missions flew by Saturn and discovered Titan's cloud layers in a near-planetary climate dominated by methane and nitrogen. With each passing decade, interest in Titan continued to mount. Eventually, the celebrated Cassini-Huygens mission set off toward the Saturn system, arriving in 2004. On January 14, 2005, the Huygens lander made its historic descent, sending back the first and to date only direct panoramic images of Titan's landscape. Titan is Saturn's largest satellite and one of the biggest in the entire solar system, surpassing even Mercury in radius, though it is less massive owing to lower density. It takes about 16 Earth days to orbit Saturn and is tidally locked, always presenting the same face toward its parent planet. Its orbital distance from Saturn hovers around 1.2 million kilometers, while Saturn itself orbits the Sun at roughly 9 to 10 astronomical units, far beyond Earth's own orbit. At Titan's surface, temperatures rest around minus 179 degrees Celsius, minus 290 degrees Fahrenheit. Although this sounds bitterly cold, in the outer reaches of the solar system, such conditions are considered relatively moderate. A thick atmosphere envelops Titan like insulating armor, maintaining a surface pressure of about 1.5 atmospheres, surprisingly higher than on Earth. Most of that atmosphere, about 95 to 98%, is nitrogen, with methane as the second major constituent. In certain areas, the methane condenses into clouds and occasionally rains onto the surface. It is precisely this dense atmosphere that makes Titan so exceptional among planetary satellites. In contrast to the near vacuum that typifies other moons, Titan's gaseous envelope is thicker than Earth's and almost opaque to visible light. That is why, for many decades, astronomers were unable to glimpse its surface through optical telescopes. Just as on Earth, nitrogen is the dominant gas. Scientists believe this abundance may stem from the breakdown of ammonia under sunlight and cosmic ray bombardment over vast spans of time. Interestingly, the temperature regime on Titan is such that methane can exist in three states: liquid, solid, and gas, mirroring water's role on Earth. This means Titan experiences methane-based precipitation, rivers, lakes, and possibly seas. Evaporation and condensation create a local weather system, complete with storm clouds and downpours that leave traces on the icy ground. Meanwhile, in Titan's upper atmosphere, complex organic molecules can form. Photochemical reactions involving solar radiation and methane generate aerosols that tint Titan's sky in shades of orange and brown, an intriguing phenomenon for those studying the origin of prebiotic chemistry. Despite the centuries-long fog, data from Cassini-Huygens has granted us a deeper look at Titan's surface. Radar images captured by Cassini reveal a network of channels and canyons that drain into vast lakes or seas of liquid hydrocarbons, primarily methane and ethane. Among them is the colossal Kraken Mare, covering several 100,000 square kilometers, resembling an ocean on an alien world. Moreover, Titan lacks the sort of hot, magmatic volcanoes we see on Earth, but scientists hypothesize the existence of cryovolcanoes, vents erupting molten water or ammonia-methane mixtures. If real, these processes could reshape Titan's landforms and influence its atmosphere. Beneath Titan's outer crust, researchers believe there may be a water ice shell, and below that a hidden ocean of water mixed with ammonia, somewhat analogous to what we suspect under the surfaces of Europa, a moon of Jupiter, or Enceladus, another of Saturn's moons. Tidal heating and antifreeze compounds like ammonia or salts could keep these subsurface layers partially liquid. Cassini's radar has also identified enormous dune fields, though their sand consists not of silicate grains, but of hardened organic particles. Meanwhile, the shorelines of Titan's hydrocarbon seas bear a remarkably terrestrial appearance, further fueling speculation about climate processes akin to Earth's. One of the central questions about Titan is whether it might harbor life. Temperatures hovering around minus 179 degrees Celsius seem unimaginably frigid by terrestrial standards, and most Earth-based organisms would perish. Yet some researchers suggest that life forms might exist that use methane instead of water as a solvent, an exotic branch of biochemistry, but not entirely beyond consideration. Nature on Earth already exhibits extremophiles, thriving in seemingly inhospitable places. On the other hand, if Titan indeed shelters a subsurface ocean of water ammonia, then in principle it could host more familiar types of chemistry, albeit well below a frozen crust. A number of scientists theorize that deep-seated processes could supply the necessary ingredients and energy for life, albeit in amounts considerably lower than the hydrothermal vents in Earth's oceans. As of now, such scenarios rely primarily on indirect data. Direct sampling of Titan's seas or ice would demand specialized missions, such as submersibles capable of exploring methane lakes or drilling rigs that could probe beneath the ice. Cassini-Huygens marks a milestone in the modern exploration of Titan. From 2004 to 2017, Cassini orbited Saturn, creating radar maps of Titan and observing its seasonal changes. In 2005, the Huygens probe descended onto Titan's solid surface, transmitting images that revealed icy rocks and a landscape shaped by liquid hydrocarbons. Looking ahead, NASA plans to send a rotorcraft drone around 2027 to 2028. This aerial explorer will move between different sites on Titan, investigating both geological structures and atmospheric conditions. Its primary goal is to detect complex organic molecules and possible chemical signatures of prebiotic or exotic life processes. Additionally, conceptual designs envision floating probes that could land on a Titan sea and study its depths like a submarine. Futuristic, yet not beyond the realm of near-future technology. Some scientists also advocate deploying a long-term orbital platform to track Titan's climatic cycles, observe how hydrocarbon sea levels change, and scrutinize the moon's geophysics in far more detail. Thus, Titan is no mere satellite adrift in Saturn's orbit. It is a genuine mini-world with its own atmosphere, climate systems, rivers, and seas, composed of methane and ethane instead of water. Research into Titan offers a rare glimpse at how extraterrestrial weather patterns and geological processes may unfold under a markedly different chemical regime. Crucially, it raises the question of whether organisms based on entirely different elements might evolve in such harsh extremes. Comparisons between Titan and Earth show that, despite vast differences in temperature and composition, certain parallels emerge: weather cycles, precipitation, surface erosion, fluid circulation, except that on Titan, fluid equates to methane. By studying these echoes of Earth-like processes, we gain a deeper understanding of life itself and the critical roles of physics and chemistry in its genesis. New missions on the horizon promise a window into this distant, wintry realm, pulling back the veil that covers Titan's ochre sky. Each fresh discovery offers a chance to witness something genuinely unprecedented, from exotic organic reactions to hints that life can assume startling and unearthly forms. While we can only speculate for now, Titan's exploration gives hope that our universe may be far richer and more astonishing than we dare imagine. Endless expanses of the solar system astound our imagination with their variety of shapes and features. Some worlds host massive plains of volcanic rock, others are shrouded in thick layers of gas, while still others are locked beneath icy shells. Surprisingly, that frozen armor doesn't necessarily indicate a dead world. On the contrary, it can hide active processes and even entire subsurface oceans. A true jewel among such mysterious bodies is undeniably Jupiter's moon, Europa. At present, it attracts the attention of many scientists because beneath its icy layer may lie an environment capable of preserving or even generating signs of life. Though Europa may appear calm and less visually striking than its volcanic neighbor upon closer inspection, it reveals a unique realm whose hidden depths hold secrets worthy of the best science fiction. Humanity gained reliable information about the four largest moons of Jupiter more than 4 centuries ago. In January of 1610, Galileo Galilei, using a telescope of his own design, spotted points of light near the giant planet that appeared to move along an orbit and occasionally disappear behind Jupiter. Realizing these were individual bodies revolving around a different center rather than Earth, Galileo provided clear proof against the geocentric model. These objects became known as the Galilean moons: Io, Europa, Ganymede, and Callisto. Over subsequent centuries, scientists studied Europa primarily through ground-based telescopes. It seemed less bright and showed lower contrast features compared to, for instance, Io. Even so, some theorized early on that Europa's surface might be a sheet of ice covering liquid water beneath. True insight into this enigmatic moon only arrived in the era of robotic spacecraft in the 1970s, during the Pioneer and Voyager missions, and subsequently through other probes. At first glance, Europa might not impress with its sheer size among solar system moons. Its radius is about 1,570 kilometers, making it slightly smaller than Earth's moon. Yet Europa's density, around 3.0 grams per cubic centimeter, is relatively high for an icy body, suggesting a blend of rock and ice. Its mass, roughly 65% of the moon's mass, is less than that of Ganymede, or even Io, yet it is ample enough for Europa's gravity to hold on to its global water ice layer. Comparing Europa to our moon shows their diameters don't differ drastically, although the moon is still more massive overall. The key difference, however, goes beyond numbers. It lies in the interior composition. The moon lacks enormous water reserves, leaning more toward a rocky crust, while Europa's subsurface is believed to harbor a vast ocean. In orbital terms, Europa completes a revolution around Jupiter in about 3.55 Earth days. Fascinatingly, it participates in the orbital resonance with Ganymede and Io. Each time Io orbits Jupiter 4 times, Europa does so twice, and Ganymede once. This resonance is significant because Jupiter's tidal forces, coupled with the gravitational interplay among the moons, warm Europa's interior, preventing it from being permanently frozen. To understand what makes Europa so remarkable, one must peer inside the moon. Current models suggest Europa has a metallic core, likely iron or an iron-sulfur mix, surrounded by a rocky mantle. The most intriguing layer, however, is its thick outer shell of water and ice. Researchers estimate this shell could be 15 to 25 kilometers thick, with the upper portion being fully frozen and the lower portion near the mantle likely warmed from below and partially pliable. A key mystery lies in the possibility that beneath Europa's solid ice crust, there is a global ocean of liquid water. Data from NASA's Galileo spacecraft, as well as gravity measurements and geological surface features, support this idea. A warm liquid environment under the ice could contain many elements essential for life, at least in microbial form. Still, whether organisms exist, there remains an open question. Notably, if this ocean is truly tens of kilometers deep, the total volume of water on Europa could exceed the sum of Earth's oceans by twofold or more. Despite Europa's smaller overall diameter, it may possess a higher proportion of water than Earth. This characteristic is the primary reason the moon commands such intense interest from the scientific community. Pioneer 10 and Pioneer 11 opened humanity's first chapter on Europa in the early 1970s. They flew past Jupiter's system, sending back only limited resolution images. It was Voyager 1 and Voyager 2 in 1979 that delivered higher quality images of Europa's surface, revealing puzzling cracks and line-like streaks hundreds of kilometers long, crisscrossing the icy crust. The real detective story began in the 1990s, when the Galileo orbiter, making multiple passes around Jupiter, performed a detailed study of Europa. It measured magnetic field variations, suggesting a subsurface saltwater ocean. Galileo also gathered data on Europa's ice composition, capturing images of large white-reddish streaks apparently formed by crustal fractures and fluid upwellings that froze at the surface, enriched by salts and other substances. Following Galileo's success, other spacecraft visited Jupiter's system in the 2000s, although none were primarily dedicated to Europa. NASA's New Horizons, which passed Jupiter en route to Pluto, and the Juno probe, mainly focused on Jupiter itself, contributed some observations. Even so, Europa largely remained an unsolved puzzle until the early 2020s, when agencies announced more targeted missions. From orbit, Europa appears almost perfectly smooth, lacking obvious mountains or craters, at least none as we know them. In reality, there are plenty of surface irregularities, but the most striking features are the lengthy colored lines and fissures that encircle the globe. Large impact craters are uncommon, indicating a relatively young surface in constant renewal. Spectral analysis shows that Europa's surface is predominantly composed of water ice, though certain regions contain sulfur, magnesium salts, and sodium. Most striking are the red streaks, places where the ice takes on orange-brown or even reddish hues. It's believed that these markings result from subterranean brines enriched with minerals. When exposed to the vacuum of space, the water rapidly freezes while the dissolved substances remain on the surface, imparting varied yellows, oranges, and browns. While the exact thickness of Europa's ice crust remains uncertain, some findings suggest it might be as thin as 10 kilometers in certain areas. Elsewhere, the ice could be much thicker. Researchers pay special attention to the relatively smooth regions with fractures, which imply that warmth occasionally rises from below, melting or softening the underside of the crust and allowing fluids or softer ice to break through. One would presume that Europa, with its modest gravity and continual bombardment by charged particles in Jupiter's magnetosphere, has little to no atmosphere. Surprisingly, some observations suggest it maintains a very thin atmosphere, primarily composed of oxygen. Clearly, this is no breathable atmosphere. The surface pressure is so low, it's effectively a vacuum. The oxygen likely arises from the dissociation of water molecules under high-energy radiation, along with charged particles hitting the surface from Jupiter's magnetosphere. Some of the resulting components escape into space, while a fraction is briefly trapped by Europa's weak gravity. Interestingly, spacecraft have occasionally detected disruptions on or near Europa that might indicate geysers or water vapor outbursts. If, like Saturn's moon Enceladus, Europa indeed hosts eruptive plumes, these could explain how its sparse atmosphere is periodically replenished and how water is redistributed from one region of the moon to another. The reason Europa stays warmer than one might expect at such a distance from the Sun lies in the tidal influence of Jupiter. The giant planet's immense mass constantly stretches and compresses Europa's interior and crust along its elliptical orbit. This tidal heating generates mechanical energy that transforms into heat, melting ice in the lower layers of Europa's crust. Orbital resonances with Io and Ganymede also play a part. Io, closer to Jupiter, experiences even stronger tidal flexing and practically boils with volcanic activity. Although Europa does not exhibit such intense surface eruptions, the gravitational tug-of-war is still sufficient to keep its lower layers warm. Ultimately, the subsurface ocean is Europa's main trump card. If it exists, then its depths could contain hydrothermal vents that supply chemical elements. On Earth, such vents teem with life that thrives without sunlight, fueling speculation that Europa might harbor similar habitats. Whether Europa could support life has intrigued experts for decades. On one hand, it lacks atmospheric pressure and temperatures friendly to earthly organisms, and its massive ice sheet presents a formidable barrier. On the other, if a vast ocean does lurk beneath the crust, it might be shielded from lethal cosmic radiation, and tidal or volcanic processes could create warm pockets that facilitate chemical reactions. On Earth, scientists have discovered microbes in unbelievably harsh environments, deep-sea vents, areas with extreme sulfur or methane concentrations, even near boiling temperatures. While none of that confirms life on Europa, it does highlight the adaptability and resilience of life forms. Consequently, Europa often appears on the shortlist of the most promising locations to search for extraterrestrial biology within the solar system, alongside Enceladus, Saturn's moon, and the subsurface zones of Mars. Acknowledging Europa's importance, space agencies worldwide are devoting substantial effort to specialized missions. In particular, NASA is developing the Europa Clipper, scheduled for launch in the mid-2020s. It will orbit Jupiter and conduct multiple close flybys of Europa, conducting in-depth analyses of its magnetic field, gravity, chemical composition, and ice structure. Simultaneously, the European Space Agency, ESA, is pursuing the JUICE, Jupiter Icy Moons Explorer program. Although its primary target is Ganymede, it also has plans to fly by Europa. One of the mission's priorities is determining the thickness of Europa's ice shell and detecting possible hotspots or plumes. Meanwhile, there are conceptual discussions about missions that would do more than just fly by. Missions that might attempt landings or even probe deep into the ice using drilling systems. Such undertakings remain highly ambitious. Drilling through tens of kilometers of hard, possibly crystalline ice is an enormous challenge. However, if future technology does make it possible, we could witness one of the greatest leaps in the history of astrobiology. Viewing Europa's map in enhanced color reveals older, darker ice regions and relatively fresh lines or areas where the surface is more geologically active. Occasionally, strange dome-like structures rise above the plains. Scientists propose these might be local upwellings of warm ice from below, known as diapirs. This presents a fascinating geological puzzle. Given Europa's modest mass, it presumably lacks large stores of radioactive elements to produce significant internal heat. Instead, Jupiter's external massaging is intense enough to keep the crust in motion, cracking, and allowing warm ice to push upward from the interior. Over millions of years, the orbital resonances likely evolve, continuing to pump energy into Europa's interior. Surface temperatures on Europa are extremely low, from about minus 160 degrees Celsius down to minus 220 degrees Celsius, depending on sunlight and latitude. In such cold conditions, ice behaves like solid rock, yet beneath the crust, heat from below may raise temperatures near the melting point. It is precisely this contrast that makes Europa's geology so striking and complex. Though Europa may seem a solitary world, it actually comprises part of Jupiter's multifaceted ecosystem. The giant planet's magnetosphere, spinning and interacting with the solar wind, creates intense radiation belts. Europa traverses these zones, subject to bombardment by energetic particles. Because of this, its top ice layers undergo radiolysis, molecular breakdown caused by radiation. Some fraction of the ejected molecules and ions could escape Europa altogether, forming a faint particle cloud around it, or even merging into Jupiter's ring and dust systems. Observations suggest that icy or gaseous fragments from Jupiter's various moons might affect the overall structure of the planet's magnetic field, potentially forming weak rings or tori of matter in the giant planet's vicinity. Meanwhile, Europa shares an orbital resonance with Io and Ganymede. Due to the 1 to 2 to 4 ratio, they periodically align, intensifying tidal distortion. Without this resonance, Europa would likely be colder and less geologically active. In essence, the entire cluster of Jupiter's moons resembles a finely tuned clock mechanism, where every cog contributes to the ongoing stirring and warming of the interior. So why is Europa unique? It's not Jupiter's largest moon, nor is it as explosive or colorful as Io, nor does it rival Ganymede's scale or Callisto's giant craters. Yet it has something that could eclipse all volcanoes and mountains, a strong possibility of a subsurface ocean. This feature alone places Europa at the forefront of future space exploration. Scientists do not rule out the idea that along the ocean floor, in areas of increased temperature and pressure, hydrothermal vents could be providing chemical nutrients. On Earth, such black smoker vents are teeming with life that survives without sunlight, lending credence to speculation that Europa might harbor similar pockets of biology. Upcoming missions like Europa Clipper and JUICE promise more insight into the thickness of Europa's icy shell and whether water vapor truly jets through surface cracks. If confirmed, these geysers may offer a unique opportunity to study Europa's ocean indirectly, sparing spacecraft from drilling through miles of ice. A probe could potentially sample the ejected material for organic compounds, salts, and minerals. Europa is, in a way, a mystery in a wrapper. Its sleek, icy exterior appears deceptively tranquil. Yet beneath the surface, processes may be underway that could reshape our understanding of life in the cosmos. And if humanity has learned this much about Europa's appearance and inner workings in a relatively short span of history, imagine how many secrets remain once our technology allows us to delve into its most remote recesses. Ultimately, exploring these kinds of celestial bodies takes us beyond conventional models. We typically look for life where there is sunlight, air, and warmth. But Europa defies these presumptions, showing that life might flourish in the darkness beneath an ice layer, constantly bathed in radiation from Jupiter. Every piece of new knowledge brings us closer to grasping not only Europa's true nature, but also the broader principles underlying the emergence of life. We can only guess at the tremendous possibilities lurking beneath this moon's icy veil. Yet it's already clear, Europa stands among the key mysteries of our solar system and might answer our most fundamental questions in biology and planetary science. If we ever confirm life beyond Earth, it could well be found here, in the slightly warm depths of an ocean hidden beneath perpetual ice. If you enjoyed this video, don't forget to give it a like and subscribe to the channel. It's the best way to show your appreciation for my work and inspire me to create more exciting content.